we look into the problem of example 5.6, which is the parallel plate capacitor case. Because of the geometry, it's two flat plates extending infinitely in the y and z direction. And the spacing between the two plates along the x direction is relatively small. Therefore, it can build up a isotropic and it can build up a homogeneous electrical field between the two plates. And as you can see, because the two plates are parallel, the voltage potential, the electrical potential, the voltage, which are shown as the dashed line here, are parallel to the plate as well. And the value of the voltage potential, the value of the voltage are larger at the top plate and becomes smaller and smaller to the bottom plate. The solid line arrows are the electrical field intensity vectors. As you can see here, it's also homogeneous, which means the electrical field intensity is the same everywhere. The magnitude are the same, and so does the direction of the electrical field intensity are homogeneous within this space between the two plates. So we can use the so according to the voltage variation, it can be regarded as a one-dimensional second-order differential equation. And the general solution for this kind of geometry is AX plus B, where A and B are constant that can be solved with known boundary conditions. And what are the boundary conditions that we have? We know the top plate voltage is V sub 0 and the bottom plate voltage is 0. So we can substitute the position, the X value, and the corresponding voltage value into this equation. We have two conditions, the top plate and the bottom plate. So we are able to solve for A and B. In this case, B equals to 0 and A equals to V sub 0 over D. So this is the V sub 0 over D is the constant for the weighting for this one-dimensional problem. And equation 5.65 here is the specific solution based on the geometry, based on the boundary condition, which are the voltage, the known voltage on the top and bottom plates. So as you can see here, the voltage, the electrical potential is a function, is a linear function of the position X and the weighting, which is V sub 0 over D. So you know it's affected. It's a function of the voltage difference and the spacing D. Then the next thing is to derive the electrical field intensity function, which can be done by taking what? Taking the gradient of V and take the negative of that. So using this equation, we found E, the electrical field intensity, can be expressed as the minus of V sub 0 over D. Note that the electrical field intensity is a vector. So it comes with the direction. In this case is what? AX direction. The minus sign means it's pointing downward, minus AX. And the electrical field intensity is proportional to the voltage difference, and inversely proportional to the separation distance between the two plates. All right, so in this slide, we get the E electrical field intensity expression. The next thing here is to find out the charge density on the top plate and bottom plate, as well as the total charge on the top and bottom plate. To find out the charge density, we use the Maxwell equation of Gauss's law of electrical field in integral form. Okay, so you can find out the total charge in a specified region. That is the top a unit area on the top plate or a unit area on the bottom plate. So as you can see here, based on this expression, the charge density at x equal to 0, that is the bottom plate, or x equals to d, can be found by taking the closed surface integral of electrical flux density. And the plot drawn here is supposed to be the top plate. So you have this imaginary box encircling a part of the top surface. And there is only the electrical flux only appear at the bottom surface of the box, because you have positive charge on top and negative charge on the bottom. And the electrical field only pass through the bottom surface. So the surface integral on top of surface and the surface on the side do not count. We only count for the electrical flux passing through the bottom surface. So you substitute the expression for D, that is the electrical field intensity E times epsilon, the permittivity. And this is surface integral. So you do the dot product of the D and the direction of the bottom surface, which is pointing upward for the top surface, pointing downward for the bottom surface. So that's the reason why here is a positive one and here is a negative one. So if you know that we are taking the surface integral of a specific surface, then you can understand why one is positive and the other is negative. So after doing that, you can have the charge density on the bottom plate is minus epsilon b sub 0 over d, where the top one is of the same magnitude but opposite polarity 所以它们的量子相同但极性不同，一个是正的，一个是负的嘛上面是带正电，下面是带负电。Alright, then you can multiply the surface area, which is unit area 1. Then here comes the total per unit area charge, total charge on per unit area. That is epsilon v sub 0 over d. So again, it's proportional to v sub 0 and is inversely proportional to d. Not. Be careful. You should notice that the total charge is proportional to epsilon. What is that? The permittivity. And we will find out the significance of this in the next slide. In this slide, we use the definition of capacitance, that is, the capacitance C is defined as the ratio of a total current, total charge over voltage difference. So in that case, for the parallel plate, C is defined as Q over V sub 0. Then if you substitute Q with epsilon V sub 0 over D and divide it by V sub 0, you end up with epsilon over D. So this is the per unit area capacitance of the parallel plate. So what is the significance of this thing? The capacitance, the per unit area capacitance is proportional to what? Epsilon, proportional to permittivity. And is inversely proportional to the separation distance D. So if you want to create a larger capacitor without increasing the size of the capacitor, what do you do? Well, you can make the two plates closer, the spacing of the two plates smaller. Yeah, that's one possibility. How about the other possibility? You can increase the magnitude of epsilon. That is, you can stuff the capacitor. You can put a dielectric of a larger permittivity within the two parallel plates. Okay, and this is critical to semiconductor to the semiconductor industry. So we have a couple of companies that is specialized in making the so-called surface mount SMD, surface mount device, the surface mount SMD capacitors. Okay, they are in the size of 0402. What does that mean? 0402. 4 millimeter by 2 millimeter. That's the surface mount element you can have in the market. You can buy that in 什么金电子还是什么 okay. And sometimes labeled with 0201. So as you can see, the length is reduced to 2 millimeter and the width is reduced to 1 millimeter. And they are actually a little bit too big. This kind of SMD components. You can have even smaller SMD components. Okay, so if you in the design of integrated circuits, you inevitably need to create capacitors in your circuits, right? The resistor, capacitor, and inductor are inevitable, okay, in creating circuits, as you have learned since your high school, right? And in semiconductor, in the environment of integrated circuit, in the environment of IC, it's not that difficult to create resistor. It's somewhat difficult to create large capacitor. So that's the reason why if you buy a CPU unit, central processing unit, and you flip the CPU, you found there are a couple of SMD elements on the back of your CPU. That's large capacitors that cannot be implemented within the CPU processor. 所以有的时候你去买那个 CPU 的单元翻过来，它背面一堆那个小小的 SMD 元件，因为那些东西的电容值太大了，你没有办法 你要在那个 IC 表面去实现它的话，会占太多空间，所以不划算，所以它宁可把它拉到外面来。好，有的时候可以看到。那像电容就更难，好，所以在 IC 里头，电阻很简单，对不起，电感很难，电容的话就还好 ，OK， 但有的时候有些大电容你还是得放在外面 ，OK， so for companies specialized in manufacturing surface mounted device, what can they do? If the capacitor size is limited, well, you can substitute high permittivity material within that space. Usually, the relative permittivity of plastic material is in the order of 2 to 4. Now, the epsilon R, the relative permittivity. And for solid material like rocks, the rocks or ceramics or pottery, it's in the range of 6 to 10. So 10 is about the largest value that you can have from naturally made material. Okay? But in order to cope with the capacitor manufacturer need, for man-made material, you can create ceramics with relative permittivity up to 100, 1,000, and even 10,000. Okay, that's what I heard of. You can have man-made material with relative permittivity up to 10,000. Okay, so that's a relatively large number. Okay, so as a consequence, you can create a large capacitance with this kind of insulation layer. Okay, so let's move on to the second property we have here. In this slide, we look into the relationship of conducting current J. J sub C, C refers to conducting current, so that's real current. And what do I mean real current? That's the current formed by electrons driven by electric potential, driven by voltages. So if you apply a voltage or you apply an electrical field onto a conductor, okay, so conducting current can only be found on conductors, which means a material with sufficiently large conductivity. So the relationship you have here is JC equals to sigma times E. Sigma is the so-called conductivity of the material. And suppose we have the same geometry, the parallel plate. Instead of stuffing the space between the two plates with an insulation layer, we put an conducting material between the two, then the same voltage difference, V sub 0, will induce, excuse me, the same voltage difference V sub 0, which ends up with electrical field intensity of V sub 0 over D, will induce a current by multiplying the electrical field intensity with the conductivity sigma. Okay, so the top equation is the current density, the current density. And as you can see, it's a vector because the currents are flowing from the top plate, which has a larger voltage, larger potential, down to the bottom plate. And if you multiply the current density with the area, In this case, is the unit area. You form the conducting current in this unit area. So the conducting current, the amount of current is sigma V sub 0 over D. The next thing is we can find out the unit area conductance. This is G is conductance, which is the inverse of resistance. And conductance G is defined as the ratio of current over voltage, which is the inverse of the definition of the resistance, which is defined as the ratio of voltage over current. So comparing to the equation shown in the slide, I over V equals to what? Sigma over D. So that's the unit area conductance of this parallel plate structure. And as you can see here, it's invariant to the amount of voltage applied on the two plates. It's proportional to the conductivity of the material in between and the spacing distance inversely proportional to the spacing D. So the smaller the spacing D is, the larger the conductance is, and larger the current if you apply a voltage. So here is per unit area conductance, and we already have per unit area capacitance, which is epsilon over D. And as you can see here, they look kind of similar, right? They are all inversely proportional to D, but proportional to the material property sigma and epsilon. Okay, so here is the per unit area capacitance, per unit area conductance of the parallel plate structure. And this, so that's the per unit area capacitance and conductance of parallel plate structure. How about the other structure? So in the following few slides, we'll look into the per unit area capacitance or conductance for cylindrical structure and even spherical structure. Okay. One important geometry that we shall look into is the coaxial cable structure. Coaxial cable, 同轴缆线, is widely used in many communication environments. The most prominent, the most likely you can see a coaxial cable is the cable TV application. Okay, I know some of you do not have cable TV at home anymore. Okay, you turn into Netflix or whatever. Okay, but it's safe to say that 10 years ago, most of the households in Taiwan have a cable TV, and it takes many years for the cable TV industry to go digital. Okay, originally cable TV signals are analog signals in the cable. So the frequency used for the cable TV is about from 10 or 30 megahertz all the way up to 1000 megahertz. So according to the definition of TV channel, each channel occupied a bandwidth of 6 megahertz. And between the channel, you have another 6 megahertz spacing. So from 40 megahertz to 1000 megahertz is divided into about 120 channels. Okay, so in the old time, the maximum limit for cable TV channel is about 120. Okay, and because the signal is analog, so different channel experience different amount of attenuation for the signal to propagate from the cable TV office or lab to your house. Okay, the smaller the carrier frequency is, the less attenuation it experiences. So that's the reason why most of the well, it's safe to say that the channel below 70, the attenuation experienced by channel below 70 are relatively mild. So you have movie channel, news channel, other entertaining channel, okay? But for a channel above 80 or in the 90 or in the 100, in the higher frequency band, the attenuation is greater. So usually they put channels specialized in stock analysis, religious enlightenment, all right, and what? And well, other channels that is not that critical to the quality of the images, right? Okay, but once it goes digital, all the 100 channel signal are compressed and modulate digitally and send up through to your house through the cable within a 6 megahertz bandwidth. Okay, using the digital modulation scheme, the 100 channel can be compressed into 6 megahertz and more. Now you have 100, 200, 600, 300, 900, all right, okay? You have more than 200 or 300 channels. They are all compressed in just 6 megahertz, okay? I remember once I go to Europe, maybe Prague, or Hungary, or Czech. They have the cable TV within the hotel ring have 9,999 channel. Okay, and I spent 2 hours going through all the channel. No, not all the channel. I spent 2 hours going through about 2,000 channels. Okay, no. So it's a shopping channel and porn, yeah, porn as well, and all kinds of stuff in about 30 languages, specialized in 30 languages. You know, no, it's Europe. Okay, so yeah, it's kind of exhausting going through 2,000 channels, and I'm not done yet. All right, okay. So you know that's the power of signal modulation. All right, I'm going a little bit off the topics. All right. So let's check out the cylindrical structure, huh? So, or even spherical structure. So here is the cross-section view of cylindrical structure. So it it's actually formed by two cylinders, one in the middle with a radius of A, and the other is on the outside with a radius of B. So you have two metallic surfaces put together to form this cylindrical structure. So in the middle, you have a larger voltage, V sub 0, and then on the outside is V equal to 0. And to the right is two concentric sphere. 其实这边写错了，应该是同心球啦，不是同心圆，同心球面啊。Two concentric sphere. So one sphere, the inner sphere is of radius A, the outer one is in the radius of B, and that you can also view the two structures as capacitors. If you apply a voltage difference between the two conductors in checking out how the electrical fields is built up. And here's one story about this one. As you can see, here's the hint, the largest transmission line in the world. Well, in the year of 1901, on December 12th at 12 p.m. Well, I think they pick up this date and time particularly. Marconi, an Italian engineer, which should be described as entrepreneur, 企业主，他自己自称是工程师啦，但他更像是一个企业主，successfully received the first transatlantic wireless message, that is radio wave sending from somewhere in England, somewhere in England to Canada, to Canada. So that's the first transatlantic transmission. The carrier frequency is a little bit less than 1 megahertz, that is 850 kilohertz, which is referred as the show wave. Prior to that, scientists claim it's impossible to implement transatlantic wireless messages because what? Because electromagnetic wave, which is similar to light, goes straight lines, right? Yeah, that's correct. Electromagnetic wave without perturbance, without external perturbance, goes straightly. And so that's the reason why physicists scientists claim that it's impossible to do transatlantic telegraph because our Earth is a sphere, So once you transmit an electromagnetic wave, it's just go to the space and you won't be able to receive it. But for Marconi, well, as long as he got sponsorship, so you attempt to, you can bump up the, you can increase the amount of transmitting power, see if you can get that. And actually, they are not the only ones who attempt to do this. There are several teams working on this project, different teams working on the same purpose. Because before this, they tried to put a long cable from Europe to America. Unfortunately, this attempt fails as well because the signal attenuation in the cable is too large that you cannot successfully send out a meaningful signal from Europe to Canada or America directly. Okay. Now, of course, we have the so-called optical cable, but they are actually relays between optical cables. Optical cables may be as long as, say, 100 kilometers long. But every few hundred kilometers, you need to build up a station that transform the optical signal back to electrical signal and amplify the electrical signal, resample and then transform it back to optical signal and put it into the next section of optical cable. That's how you do this for transatlantic signal transmission. And why? Why do they receive the signal from England? Because above the atmosphere, well, actually this is part of the atmosphere. It's a so-called ionosphere. 电离层 ionosphere. Well, as the name suggests, in the ionosphere you have positive ion and negative ion. So the ionosphere is conducting, slightly conducting, because it comprises both negative and positive charge. So it has certain conductance, but it's not a good conductor. Okay, it is not a good conductor. Why do we have ions in this high altitude? Because of the sun. Okay, the radiation from the sun, which comprise not only the visible light, it comprise X-ray and gamma rays as well. Those high frequency electromagnetic waves can ionize gas molecules, so that the gas molecules separate into positive and negatively charged particles. So you have the ionosphere. So some of the electromagnetic waves going this way get reflected by the ionosphere. Okay, so it's bouncing up and down between the Earth and the ionosphere. So that's the reason why I referred the Earth as well as the ionosphere as the largest transmission line in the world. In this world, okay, in the world you live, okay. All right. So Marconi not only received a lot of money, he also received Nobel Prize 8 years later. All right. And here are the some critical parameters associated with parallel plate structure, coaxial cylinder, and concentric spheres. So you can go through them one by one. Okay, so for the parallel plate, you have voltage applied on top and bottom plate. You have general expression for this 1D problem in rectangular coordinate system. You apply the boundary condition, I mean the top plate voltage and bottom plate voltage. You can solve for the specific solution. You have the voltage V, and taking the gradient, you have the electrical field intensity expression. Taking the surface integral, you have the charge density and the total charge. And use the definition for capacitance, you end up with per unit area capacitance. and for concentric, and for cylinders, coaxial cylinders. The Laplacian equation for cylindrical coordinate system is different from this one. So again, this is a second order differential equation, but you need to be careful about R, okay? And the general solution for coaxial geometry is V equals to A times log of R plus B. Okay, so it's different to rectangular coordinate system. As a result, the voltage, the specific solution for the voltage is different. And the expression for the electrical field intensity, which is acquired by taking the gradient, is different as well. But the processing steps are similar. Okay, so you can still derive the expression for uni-area capacitance, your uni-length capacitance. Again, the capacitance is proportional to epsilon, the permittivity of the material in between, and is related to the geometry. So here is the B over A ratio. So if you want to increase the capacitance of your coaxial cylindrical structure, the B over A ratio should be smaller. So that means the value between A and B should be closer. The V over A ratio should as closer to 1 as possible. And here is the concentric sphere. So again, the Laplacian equations are different in this case. So you end up with different general solution. The general solution for spherical coordinate system is A over R plus B. And again, you can solve it by substituting boundary condition. So this is specific solution for voltage, for electrical field intensity, for charge distribution, and here is the capacitance for this spherical structure. Again, it's related to material property and geometry. All right. And here is, let's begin with section 5.4. So let's now consider the three arrangements shown below. We already discussed about the capacitance, conductance, and here is the configuration for us to find out the per unit length inductance 电感所以最右边是要找电感的。And capacitance is related to what EM properties? Permittivity. Conductance is related to what? Conductance. So inductance is related to what? Permeability mu. All right? Now, and permeability mu is related to magnetic field. Now, so to find the per unit length inductance, we will change the problem a little bit to currents on this coaxial cylinders, currents on the coaxial cylinders, and the magnetic field intensity H built up within this space. Okay, so mu, the permeability, is more critical here. So here we have currents. This one is flowing outward out of the screen, so it's represented with dots. And the cross on the outside outside cylinders flows into the screen. Okay? The total amount of the currents are the same. The total currents the total current magnitude are the same. In other words, the current density inside and the current outside are different. Okay? So the total currents can be expressed as current density times the circumference of the cylindrical structure, 2 pi a. So let's put JA over here. And it should be the same as JB times 2 pi B, right? So the current density in the inside cylinder should be somewhat larger than the one on the outside. And well, we still should begin with capacitance. All right, so here is the result according to the table. The per unit length capacitance divided by total capacitance divided with the total length L equals to 2 pi epsilon divided by log of B over A. That's the per unit length capacitance. And as to the conductance, you apply a voltage difference V sub 0 between the inner and outer conductors. And similar to the derivation of the capacitance, the current density is expressed is derived with the multiplication of conductance sigma with electrical field intensity, which has been derived in the previous slide. So it's sigma times V sub 0 divided by R times the log of B over A. And if you divide it, the total current will be JC times 2 pi 2 pi A or 2 pi B. Okay. The total current will be JC times 2 pi R. Okay, JC times 2 pi R. And total current divided by V is your conductance. Okay, so you end up with 2 pi sigma over log of B over A, which is quite the same as per unit length capacitance. It's expressed as 2 pi epsilon. So here you have 2 pi sigma, okay? And the denominator are the same. So let's stop here and continue with page 29.